Hello everybody. Last class we were discussing about the different theory associated with the solidification casting process. So there we try to understand the phase diagram or what way the concentration varies as per the solidus and liquidus line. Now we'll try to look into little bit that in terms of the grain structure, what type of solidified cast structure we can expect when you in a casting process, typical casting process. So we start an example with the sand molding, or we can say the casting using a sand mold. So there the rate of the heat transfer are different, or in structural component can be different depending upon the cooling rate. So if you look this particular figure, that different types of the grain structure, we can observe that the mold wall, you can see that at the mold wall, that almost starting the first starting point of the nucleation near the mold wall, and almost equal size equiaxed kind of the grains is usually formed, and all the mold wall you can see observe the equiaxed grain in the usually formed on the mold wall. After that, once it is done, then there is a the grain grow occurs in particular direction. So that is called the columnar grains. It's a long and elongated grain, one particular orientation it occurs, and it might happens extend up to the center point of this thing. So here you can see the apart from the grain near the mold wall equiaxed kind of the grain, because at the same time so many nucleation forms here and creates almost equal size of the grains, of course within the equal size of the grains, and then there after that it's try to grow perpendicular to the mold wall, and it creates kind of the columnar grain because maybe heat extraction or temperature gradient one particular direction is the maximum. So that is the maximum in the sense perpendicular to the mold one. Overall we can see that. Then it can extend up to the central line, but this is the usual practice, we can see that, but it may happen so exactly at the center point also there might be happening some kind of the equiaxed kind of the grain structure. We will see, we will take the another example of the of this particular situation. Now here we are trying to describe the ingot structure, and this typical cast structure, and this in the typical cast structure we can expect that here it is little bit different, that outer chill zone of the equiaxed crystal, so that is near about the mold wall, so that is the most chilled zone. Then next zone is the columnar zone of the elongated grain we observe in this particular structure, and then central equiaxed zone. Actually central equiaxed zone, here it entirely depends on the what type of the cooling rate of the cooling, or basically the temperature gradient exists. Based on that it can form completely in terms of either equiaxed grain and the mold wall, and remaining can be the columnar grain, or at the middle point there might be having some kind of the equiaxed zone. So in a typical ingot structure is basically having these three parts are there, and we try to explain the individual part. First is the chill zone. Chill zone means is basically trying to indicate the near the mold wall. So when liquid is in contact with the cold mold, so therefore immediately it follow kind of the rapid cooling. So near about the mold wall, all that you can expect that the almost nucleation start throughout this this in contact with the mold wall, and here it's with a very thin zone, it's a small zone, it creates all the almost equiaxed kind of the grain. And in this case, because here the rapidly cool below the liquidus temperature when it is in contact with the mold wall. So I mean to say the cooling rate here, the rapidly cooling, but that the cooling rate may not be that much of rapid in the remaining zone also. So therefore mainly the solid nuclei form and grow into the gradually to the liquid, but as the mold wall is gradually warm up, that means when it is in cold mold is start transferring the heat, when it is contact with the molten metal, then mold wall gradually warm up, and it is possible to solidify, break away the solidified crystal. Some crystal may be breaks also during this particular process, and of course at the same time there is a temperature gradient or concentration gradient also is there, and that actually induce some kind of the turbulent melt, that means flow might be in the turbulent. So, there is a material flow occurs and it is a very localized zone. The material flow occurs from transported from one point to another point, and it helps to some part is the break away of the already solidified component, and because in this way it's influenced the solidification behavior. So, for the characteristics of the chill zone is that you can see that actually the overall solidified structure depends on the pouring temperature. For example, pouring temperature, there is the liquid not having much superheat, and when you pouring the liquid, it's very close to the melting point temperature only. Then overall melt volume with the rapid cooling might be following. So, when it is a rapid cooling might be following, in that case throughout this volume there is a big bang nucleation occurs and almost produce the entirely aqueous ingot structure. So, that is the most important, because your initial pouring temperature is low. So, pouring temperature of the molten metal is low in the sense that it is just above the melting point temperature. So, in that case we can expect kind of the aqueous ingot structure, but there is also a risk in the sense that pouring temperature is too low. So, it may not, before filling the complete mold cavity it can solidify. So, overall we can get some kind of the other kind of the defect. So, then not be each and every point within the mold, if it is a very complex structure, will not be filled by the liquid metal if pouring temperature is low. This is the other part, but in terms of the solidification behavior, if the pouring temperature is low, we can expect the maximum part of this melt volume or mold volume will be occupied, is very close to the aqueous kind of the ingot structure, and that is following the big bang nucleation. Means throughout this process the nucleation starts throughout the structure at the same time. But other way also, if the boiling temperature is very high, that means superheat is much high for the liquid metal, in that case in the center ingot remains above the liquidous temperature for a long time. That means it takes much more, center point which takes much more time to solidify. So, there is a chances much more remelting to occurs during crystal. So, starting the solidifying, making particular component, because there is a variation in the heat flow also, then remelt of the already solidified component may occurs, and it actually break and it influence the nucleation process as well as the complete solidification process. So, now see that this is the typical characteristics of the ingot structure and specific to the chill zone. Now, if we try to look into the columnar zone, so then the next part, this thing here, this first one is the chill zone. We can see this part, and now this is the columnar zone. So, that is it's a columnar structure, it will try to follow. So, here in this case, after pouring, temperature at the mold wall is definitely, it will try to decrease, and then crystal actually grow in the chill zone, and in that after going the chill zone, then it will try to go perpendicular to the mold wall, and it's sometimes in the certain preferred direction it will try to grow in this particular. Preferred direction means it actually depends on the, for example, types of the crystal structure. So, for example, cubic crystal, this usually grow 100 in particular direction, in that is the preferred direction of the grow perpendicular to the wall. So, therefore, in this case usually close the direction of the heat flow, that means the perpendicular to the mold wall, in that direction it will grow very fast, and that is mostly the preferred orientation of the 100 direction for a particular cube crystal structure. In case of cubic crystal structure, there is the 100 is the that particular direction, but at the same times that outgrow less favorably oriented direction. It means that the other lateral direction the growth will be very minimum. So, that is why we can expect in this case that one preferred direction. So many parallel columnar grains will try to form, but growth in the lateral direction is very low in this case, in this particular case. So, what with this growing with this particular structure in this columnar zone, it actually leads the formation of the columnar grains in 100, that is almost parallel to the columnar axis. So many that we can observe from figure also, but each columnar crystal contains mainly the many primary dendritic arms. So, it's might that it's a, suppose this is the columnar grains one particular direction, it might be having some dendritic structure, So, but it might be having the mainly the primary dendritic arm will be much bigger as compared to the secondary, or ratio will be much more as compared to the secondary dendritic arm. So, therefore, volume fraction of the solidified part actually increases with increasing the distance behind the tips of the dendrites, and mainly the single phase material. So, volume fraction increases behind the tips of the dendrites. So, this is the tips of the dendrites, and that is because of the increasing distance of the tip of the distance, the volume fraction is actually increases. But secondary and tertiary dendritic arm adjacent to the dendritics is actually basically when you this one dendritic arm for secondary arms is there. So, this is another dendritic, this secondary. So, it is a very kind of network kind of things we will try to follow, and there is a possibility of entrapment of the liquid metal between the dendritic arm. So, therefore, this is actually containing the many primary dendritic arms, liquid may flow. Each actually in that when it happens in this kind of the networking thing. So, we can expect the solute concentration in the liquid zone and solute concentration in the already solidified zone might be different, and we know that it is a non-equilibrium condition when there is a solidification occurs, definitely in case of the alloy system. So, there we can observe that the anyway concentration of the solute concentration of the liquid phase is much more as compared to the solid. So, that concentration gradient always exists during process, and that actually influence the further the structure and solidification behavior of this this particular zone. So, further on to the columnar zone is that the zone between the tips of the dendrite and the point where the last drop of the liquid solidify, that zone is practically measured. This indicate these are the Musi zone. Musi zone means that we know that it is a mixture of solid and liquid zone, but here theoretically we can define the between the region tips of the dendrites and the last drop of liquid where it solidify, that zone is the Musi zone. So, definitely the length of this zone is, it depends on the temperature gradient, what is the that we have already shown the in the solidification. Always when you try to understand the constitution supercooling, always we are looking into what is the temperature gradient ahead of the solid liquid interface. So, that is the one parameter, and at the same time it depends on the non-equilibrium freezing range of the alloy. Freezing range means the ideally the between the liquidus solidus temperature range, or in case of the non-equilibrium freezing solidification, there you can find out that this solidification terminate at the solidification terminates exactly at the eutectic temperature. So, therefore, it depends on this, that temperature is much more, then in that cases it actually having some kind of the a different kind of the behavior, we can expect the different kind of the behavior in the solidification of this particular alloy system. Now, secondary arms becomes coarser with the distance behind the dendritic tips. So, secondary arms becomes coarser. So, that means, so suppose this is the primary arm, then secondary arm is follow. So, behind the tip, so if this away from the tip, this secondary arm becomes more coarser because it is having much more time. So, it actually size becomes much more, it becomes more coarser, the secondary dendritic arm. Now, primary and secondary arms spacing also increases. So, spacing gap between these two primary primary and the spacing between the secondary arm and spacing between the another primary arm. So, that actually also increases with increase the distance from the mold wall. So, away from the mold wall, this gap actually gradually increases. I mean to say that near the mold wall, this the gap is less, and away from the mold wall the gap is much more. So, that is why the primary and secondary between the secondary dendritic arm. So, therefore, entrapped liquid is low, or maybe it will try to solidify and becomes more thicker here, but here the near about the tip, the in the zone between these two, we can expect much more liquid till awaiting for the solidification. So, therefore, corresponding to decreasing cooling rate and with the after time rate with the time after curing. So, this happens because cooling rate is gradually decreases when the dendritic tip grow one particular direction. So, from here to here, so near to the center zone, the cooling rate is gradually increases away from the mold wall. So that is why this type of structure you can expect, and typical characteristics of the primary and dendritic secondary arm is also obvious during the solidification process. Now once we reach exactly at the center, then we can expect certain part equiaxed zone, but equiaxed grains is actually randomly oriented at the center and almost okay. In this case, if you remember last class we were discussing that, although that I am just taking back to this particular, here you can see that almost the equiaxed dendritic structure, here equiaxed dendritic structure, it is more clear. Here the dendritics forms, but it is a almost equiaxed structure. So in this case dendritic, but here also dendritic form, but it is a kind of the columnar structure, it is oriented one particular direction. So here is the almost equiaxed structure and here the columnar structure, but both within that we can find out both the dendritic primary arm, secondary arm, all are there, but they are structurally they are different depending upon the cooling rate we are following. So therefore in equiaxed grain zone, origin of this grain is basically melt of dendritic side arm. So some part already, because of the high convection current, the certain part of the dendritic arm is a break or melt off. Again it is a melt down, because we observe that there is a heat transfer occurs from solid to liquid, temperature might increase also locally, and then that actually try to melt the dendritic arm. So therefore in that case, if temperature around dendritic actually increases near the dendritic arm, this actually causes the melt and detach from the main stem. So near about, so temperature is much more, so near about when try to grow this thing, so it's melt the dendritic arm, again it mixed up with the main stem, detached from the main stem and mixed up with the liquid. So therefore it modify the concentration of the liquid. So therefore finally an effective source of the suitable temperature pulses is provided by the turbulent convection current. It means to say that concentration gradient will try to make the movement of the liquid or transport of the liquid from one position to another position. So it's a that actually creates that turbulent convection current, and because of that the variation of the temperature also occur. We cannot expect the very uniform temperature there. So variation of the temperature from one point to another point, that might also happen. But overall if you see that that equiaxed zone, here we can see that almost the zone that at the same time the nucleation occurs in the several positions, and then if there at the same time nucleation occurs in this particular zone, all this position, so it will try to grow and then the competitive grow. So then therefore here almost, but the gradient variation is not much more, so almost having the equal chances to grow, and when it is like that situation, then more or less the equal size of the grains is actually formed at the center part. Okay. And of course we can expect the center part rate of the cooling, and it's completely different from the mold from chill zone and the columnar zone. So that's why these are the typical kind of the structure you can observe, and it's a very typical associated with the any kind of the casting process. Now we do further analysis of the ingot structure, but overall we can see that there is some shrinkage effects will always be there, because when there is a change of the phase from liquid phase to when it is solidify, then liquid phase to solidify, then we can expect some kind of the shrinkage of the metal volume during this process, but usually shrink most of the maximum of the most of the metals. Now during the shrinkage, when shrinkage happening in case of the alloy, and there might be having low freezing range, the narrow freezing range. So freezing range means the solidus and liquidus temperature is very close or not much difference. So in that case, so therefore Mussey zone will also be narrow. So because solidus and liquidus temperature is low in this set. In that case, when solidification completes, the ingot contains deep central cavity or pipe kind of the defects is usually observed. So at the center point, we can expect some kind of the pipe or central cavity because of the shrinkage effect by changing the phase from liquid phase to solid phase and during the solidification, and that usually happens metals is having very low freezing range. But in other way also, if alloy having wide freezing range, in that case Mussey zone can occupy the whole ingot. So therefore the motion size will be much bigger in that cases. So therefore in that cases usually you don't expect any kind of the central pipe like other cases we observe, this may not form also. So in that situation the liquid actually having a flow down the compensates for the shrinkage of the dendrites. So that means in that case we can give the some space available between the different dendritic arms. So when there will be shrinkage will occurs, so liquid metal will try to flow and compensate that the shrinkage before termination of the solidification. So therefore in that case the interdendritic channel is there and close up the liquid flow and but this may happen so that interdendritic channel is basically forms, and when dendritic grow too much, then interdendritic spaces will be occupied, maybe obstructed by the formation of the dendrite, and in that case there is a difficulty of the filling of the compensation from the flow liquid from the other side. So in that situation it will try to create some kind of the small voids or pores can be created, but not like a very big central pipe or kind of the central cavity in case of the low freezing range material. Now once we look into these things, therefore the one of the defects usually occurs in the casting process during solidification of the casting, that is the segregation. Segregation is basically simply the changes of the composition over a particular distances in a solidified structure. Now two types of the segregation, one is the macro segregation, it means that composition changes over long distances, or micro segregation is the scale of the scale are different, in this case a scale in the form of a secondary arm spacing. In that scale the over that particular length the segregation occurs. So why this segregation is comes into the picture, because we observe that during the solidification there is a change of the composition may also happen during the solidification, and specifically in case of the alloy system. So alloy system we observe the composition of the liquid changes, composition of the solid changes, but composition of solid changes is little low, but composition of liquid changes is much more during the solidification process. So when there is a composition of liquid change and availability of the liquid, and then may create some kind of the segregation, that means changes in the composition during the solidification might also happen, and that is termed as the basically segregation. Now macro segregation means over the large scale, over the large position, large distances, long distances, these changes of the composition is observed. Now large difference in the composition arises across the dendrites due to the non-equilibrium phase in the last solidifying drops. Of course we observe the across the dendrites when the presence of the during the non-equilibrium phases, and usually happens in the last solidifying drops of the liquid. So we can see that gradually decreasing the solidification temperature, but when the almost complete solidification, but there is a say maybe we can assume in the last drop of the liquid phase that liquid composition is much more as compared to the already solidified. So at that position then composition might changes across the dendrites. So in that cases cooling rate might not happen the dendritic spacing too much of course, but that is why it does not change much the solid concentration. So basically cooling rate is only affect the whether it is finer structure or coarse structure, or finer dendritic arm or the coarse dendritic arm will form, that is only influenced by the cooling rate. So therefore, but this kind of the segregation micro segregation is not having much influence by the cooling rate, and of course this ensures the applicability to wide range of the cooling rates is practically. So therefore segregation may happen such way such that the similar kind of the segregation might be happen over a particular wide range of the cooling rates in practical. Now what are the factors responsible for the macro segregation? So macro segregation we can see these are the different points we think we can look into, and for the macro segregation what are the factors? First is the shrinkage due to the solidification, that means change of the phase from liquid phase to solid phase, and of course thermal contraction might be happen. So you know that each and every material thermal expansion coefficient is much more, that is associated thermal contraction will be much more in that case. So both are responsible for the macro segregation. Apart from that, density differences in the interdendritic liquid, So the liquid trapped within the interdendritic spaces, the density might be different from the remaining liquid. So that actually influence in macro segregation, and of course density differences with the liquid phase and the solid phase. And convection currents driven by the temperature induced density differences. So of course temperature induced density differences might be happening. Temperature density difference means we know that there is a density of the solid and liquid phase are different. So that it means that temperature having role influence there is a changes in the density. So that's why temperature induced density differences in the liquid phase also create some kind of the convection currents, and this also responsible for the creation of the one of the factors for the macro segregation. So these four factors are important to look. These are the all four factors are basically overall create the macro segregation. Now sometimes the shrinkage effect. So when there is a shrinkage effect occurs during the liquid during solidification, that actually creates kind of the inverse segregation. But columnar dendrites already becomes thicken in the solid rich liquid, assuming K less than 1 means that we use the usual the concentration versus temperature diagram. For that purposes K is less segregation, that K is 1 less than 1, and in that case there must backflow between the dendrites to compensate for the shrinkage, and at the same time it raises the solid concentration relative to the center. So with respect to the center, when there is a solid rich liquid flow on the near to the dendrites, so basically there is the rises the concentration of the liquid as compared to the center. So this concentration difference is basically creates kind of the macro segregation. So this effect actually observed in case of the having wide range of the wide freezing range. So for example, in case of the aluminum, copper and copper tin alloy, they are having the wide freezing range, and we can observe this kind of the changes in the composition, the center and the interdendritic spacing. So that actually influence the creates some kind of the macro segregation. Even gravity effects is also responsible in interdendritic liquid flow, and for the equiaxed crystal formation the gravity also play an important role. But overall if we look into this thing with respect to all the factors responsible for creating the macro segregation is actually very complex. The complex pattern we can observe in a structure that actually create the macro segregation. And remember, the macro segregation is actually occurs, you see it's the concept most of the cases the concentration gradient or concentration gradient existent over a very localized position. Now similarly we can look into the segregation in continuous casting process also. So in continuous casting process we can see that there is a continuous pouring of the molten metal in a copper cooled mold, water cooled copper mold, so that high rate of the heat transfer occurs through the copper. But it is maintained in such a that there is a continuously feeding of the molten metal here with the mold, and it creates at the same time the there is output is the continuous looking of the solidified component here. So in this case, so therefore the speed of the solidified component is basically analogous to the what we can maintaining the growth of the solid liquid interface in this case maintain, and that decides the speed of this thing, that output of the this solidified strip. Here you can see this is a molten metal, it creates some, it's a liquidous and solidus zone. So Musi zone here, and it's a solidified plate, and solidified is the output. So therefore it's a kind of steady state situation, that what is the rate of the flow molten metal is added and what is the rate of the output, such that it will maintain the constant the solidus and liquidus this line in the position of the solidus and the liquidus line, and the solidifying from liquid to solid. So here in practice the speed of the withdrawal is definitely it's analogous to the solid liquid interface is maintained, but practically the hydrodynamic effect allows the tendency for the flow line. So this actually flow line and fan outward, and that will try to produce some kind of the segregation, negative segregation effect near the center. So near the center you can see the negative segregation occur because of the hydrodynamic effect. So, in case of the continuous casting process. Now, if the orientation of this thing is something different where we can eliminate the effect of the gravitational effect, in that case there might be possibility of the central line segregation is usually happens in case of the continuous casting process, or it is a kind of the problem or issue associated with the continuous casting component. So, herefore, surface zone is mostly made up of equiaxed crystal. For the similar way, the surface part is the equiaxed structure. The surface zone is then follow the columnar zone, and in the very center the equiaxed zone. The similar kind of the structure here we observe, even the in this case is the equiaxed zone near about the mold surface, then columnar, then the equiaxed zone. So, that is the typical structure of the even for the continuous casting process. But in this case the process of the continuous casting is features are different, kind of the segregates might be there, where most common in the segregation effect is the central line segregation. This is the most serious problem associated with the continuous casting process. At the central line we can find out the segregation, it might be macro segregation, it might be the micro segregation. So, segregates are mainly concentrated to the center, so that create kind of the micro segregation, but at the same time macro segregation may also happen associated with the continuous casting process. Now, overall if we look into the segregation in ingots and casting process, we can see of course segregation is a undesirable because it is having the some adverse effect in the properties. So, mechanical properties definitely, because there is a composition changes in a structure, inhomogeneity in the creates some kind of the inhomogeneity in the structure that will influence impact on the mechanical properties of the cast product. But if it is the micro segregation, that can also be mitigated by the homogenization treatment, heat treatment process. So, in that case it can be mitigated, but macro segregation is basically happens over a long distances, and diffusion in the solid is far slow. In case of the that will not be able to completely remove the macro segregation. So, macro segregation is only possible to control if we control the solidification process. During the solidification process we can avoid that, we can control the macro segregation process, but after any kind of the post treatment process, that it is hardly possible, it's basically it's not possible to remove the macro segregation any kind of the post treatment process, but micro segregation can be removed kind of the heat treatment process. Here we will try to see some kind in casting process, that it is a typical structure we can see in this case, that for example that to visualize the what way it occurs, the solidification front moves in case of the casting process. We see, first looking to the picture, this is the sand mold. So, sand mold, and this part is already solidified part. So, it is initially filled with the liquid metal, and there is the particular time, this is the solid liquid interface, and here is the liquid metal, and this is the typical structure or the solidification process associated with the casting process. So, the center liquid metal is there, and some part definitely some solid liquid interface will also be there, solidified component, and the outward it is holding by the sand mold. Now, here you can see further that how it works. We can see there is a, when during the cooling process, transformation of the liquid into the solid. So, grey color is gradually solidifying, and you see the liquid transforming, and this is the typical shape, and gradually it is now it is completely solidified component associated with the casting process. So, here this simulation is very we can understand that starting from the mold wall and gradually moving and towards the center point, and because center point becomes last the point where it solidifies. So, center point is the last point where it is solidified. Of course, it depends on the shape of the structure also, but we have considered it is a very simple shape just to understand the what way the solidification occurs during the casting process. So, we can see another example also. So, here is the microstructure evolution at the different cooling rate. Try to do some simulation here, and we observe that micro segregation of the solute elements is occurs between the dendrites. So, micro segregation that can be done through the simulation process. I think they utilize some kind of the phase field model. Now, you are familiar with this thing, this particular diagram, that we follow the growth rate and the temperature gradient this direction. You can see this is the different zone, the low values of the G by R and high values of the G by R, the planar structure, cellular, columnar dendritic equixt. But at certain point the columnar dendritic structure is to cellular grain morphology is observed and on increasing the cooling rate. So, if you know this is the this is the high cooling rate alpha 2 and this is the low cooling rate. So, when there is a cooling rate is increasing, the morphology can change from the columnar dendritic to the cellular structure if in this process. So, that actually indicates the phase transformation path from columnar dendritic to the cellular dendritic cellular structure and upon increasing the cooling rate. So, this line indicates the different cooling rate. So, this actually indicates the gradually it is increasing this direction, the cooling rate is actually increased. So, this is the indicative of the different cooling rate. Okay. Now, at different cooling rate here it indicates the alpha equal to 0.1 Kelvin per second. So, this is the typical structure that how dendrites forms here in this particular this thing, and composition changes. X axis represent the weight percentage of the gadolinium GD, and this different this dendritic arm actually grows in the simulation we have shown here. So, this alpha equal to 0.1 Kelvin per second, it's here you can see that cooling rate is actually very slow cooling rate. And figure B we see observe alpha equal to 0.2 few little more that we can cooling rate, and here you can see, and when alpha equal to 1 Kelvin per second and another alpha equal to 2.5 Kelvin per second, that means all the cases gradually there is a increment of the cooling rate. We can observe that there is an increment of the cooling rate. We see the primary dendritic arm size is much more in this columnar structure. So, dendritic arm is gradually high cooling rate means dendritic arm is the length of the dendritic arm is much more as compared to the low cooling rate. Now, this is the one observation, and other observation is that we can observe that particular cooling rate when making the dendritic structure. So, the element segregation actually happening in this particular zone. This is actually dendritic here. This is the blue color is basically dendrite, the solidified part actually the dendritic part, and between these two we can see this color is little different. We can observe the color is little different. So, here you can observe some kind of the element segregation is actually occurs in this particular this process. Okay. So, this is just an example that the segregation may also happen at the that between some interdendritic spaces the segregation may happen also, and that actually depends on the when there is a change of the transformation path, one path to another path, and element segregation happen because of there is a concentration difference. This is just an example for this particular purpose. So, I think that is all, and here we have discussed the solidification, the basic elemental solidification associated with the casting process. So, thank you very much for your kind attention.